Welcome to Quantum on the Treadmill. Hi, everybody. Welcome to Quantum on the Treadmill. This series began with a simple decision a while back. I decided that if I was going to spend an hour a day on a treadmill, I wanted to exercise my mind as much as my body. Instead of watching television or scrolling through my phone, I started asking questions about quantum mechanics. The problem was every explanation I found seemed to assume I already understood the mathematics, but I wasn't looking for equations. I wanted the story. I wanted to know how we got here. Why did Max Planck introduce the quantum? Why did Einstein believe light could behave like particles? Why did Niels Bohr think electrons occupied discrete orbits? What inspired Louis de Broglie to ask whether matter itself could behave like a wave? And how did those ideas lead to Werner Heisenberg, Erwin Schrödinger, Max Born, and the birth of modern quantum mechanics? That's when AI became my treadmill companion. Every workout became a conversation. I'd ask a question, AI would answer it. I'd challenge the answer, ask another question, and we'd keep digging. Before long, I realized I wasn't just learning quantum mechanics. I was following one of the greatest detective stories in the history of science. Along the way, AI became much more than a tutor. It helped me organize my thoughts, build outlines, write scripts, generate artwork, suggest visuals, and automate much of the creative process. In many ways, this entire series was conceived, researched, and produced while I was walking on a treadmill. This series isn't about making you a physicist. It's about making quantum mechanics approachable by telling the story behind the science. We'll start with Max Planck and a crisis that no one could explain. From there, we'll follow the trail to Albert Einstein, Niels Bohr, Louis de Broglie, Werner Heisenberg, Erwin Schrödinger, Max Born, and many of the remarkable scientists who transformed our understanding of the universe. We'll spend less time memorizing formulas and more time asking the same questions they asked. We'll look at the experiments, the debates, the wrong turns, the breakthroughs, and the moments that changed science forever. So whether you're on a treadmill like I was, out for a walk, driving to work, or just curious about how the universe really works, I hope you'll join me on this journey. Welcome to Quantum on the Treadmill. Let's start walking.
What if one experiment could change everything? Imagine you're a scientist in the late 1800s. You believe you've finally figured out what light is. The greatest minds in history agree with you. The mathematics works beautifully. Every new discovery seems to reinforce the theory. Then a simple experiment refuses to cooperate. Would you abandon everything you thought you knew, or would you try to explain the experiment away? That question lies at the heart of one of the greatest scientific revolutions ever told. For nearly 3 centuries, physicists weren't really arguing about what light was. They were arguing about what experiments forced them to believe. Every generation encountered observations that contradicted the previous generation's best explanation. What emerged wasn't simply a new theory of light, it was an entirely new way of thinking about reality. Newton's elegant answer. In the 17th century, Isaac Newton imagined light as a stream of tiny particles traveling through space, and it was a compelling idea because it matched everyday experience. Light travels in straight lines, it casts sharp shadows, it reflects cleanly from mirrors. Tiny particles could explain all of that. For many scientists, the case seemed closed. Then came 2 tiny slits. In 1801, Thomas Young performed one of the simplest and most devastating experiments in the history of science. He cut 2 narrow slits in a barrier and shined light through them. If Newton was right, the result should have been obvious. 2 streams of tiny particles should produce 2 bright bands on the screen behind the slits. Instead, the screen filled with alternating bright and dark bands. The result looked exactly like what happens when 2 sets of water waves overlap. Where 2 wave crests meet, they reinforce one another, producing a brighter region. Where a crest meets a trough, they cancel each other, leaving darkness. This phenomenon is called interference. Particles don't naturally interfere with one another. Waves do. Suddenly, light looked much more like a wave than a particle. Diffraction makes the puzzle even bigger. Then came another surprise. When light passed through a very narrow opening, it didn't simply continue in a straight line. It spread out and bent around edges. This behavior is known as diffraction. Water waves do this. Sound waves do this. Particle-like objects generally do not. With every new optical experiment, evidence for the wave theory grew stronger. By the late 19th century, many physicists believed Newton's particle theory had been left behind. Maxwell appears to settle the debate. Then James Clerk Maxwell unified electricity and magnetism with one of the greatest achievements in theoretical physics. His equations predicted the existence of electromagnetic waves. When physicists calculated the speed of those waves, the answer matched the measured speed of light almost perfectly. It was an astonishing triumph. Light wasn't merely acting like a wave, it appeared to be an electromagnetic wave. The debate seemed over, or so everyone thought. Then reality refused to cooperate again. At the turn of the 20th century, physicists encountered another stubborn experiment. Hot objects emitted light in ways that Maxwell's wave theory simply could not explain. The mathematics predicted something absurd, an infinite amount of ultraviolet radiation. Nature clearly wasn't doing that. Max Planck reluctantly proposed a radical solution. Perhaps energy wasn't emitted continuously after all. Perhaps it came in tiny, discrete packets. Planck believed this was simply a mathematical trick, a temporary fix that would eventually disappear. Instead, it became the first crack in classical physics. Einstein pushes the crack wide open, and only a few years later, Albert Einstein studied another mysterious experiment, the photoelectric effect. Certain observations simply couldn't be explained if light were only a wave. Einstein proposed something extraordinary. Sometimes light behaves as though it arrives in individual packets of energy, what we now call photons. Now physics had an entirely new problem. Interference and diffraction still showed unmistakable wave behavior. The photoelectric effect showed unmistakable particle behavior. Neither picture was sufficient by itself. The experiment that refused to go away. Scientists returned to Young's famous double-slit experiment, but this time they performed it differently. Instead of sending a continuous beam of light through the slits, they fired individual photons, one at a time. If light were truly made of particles, each photon should pass through one slit or the other. Yet after enough individual photons struck the screen, the familiar interference pattern slowly emerged. It was as though each photon somehow contributed to a pattern that only waves should produce. Even stranger, whenever scientists measured which slit a photon traveled through, the interference pattern disappeared. The very act of obtaining information changed the outcome. Nothing in classical physics prepared scientists for a result like that. The real debate. Looking back, it's easy to think the argument was simply about whether light is a wave or a particle. But history tells a richer story. The real debate was never about choosing sides. It was about confronting experiments that refused to fit either description completely. Every time physicists believed they had solved the mystery, nature answered with another contradiction. Wave-particle duality wasn't invented because scientists enjoyed paradoxes. It was forced upon them by experiment after experiment. Reality refused to fit comfortably inside the categories that humans had created. That realization became one of the first great steps toward quantum mechanics, a theory that would forever change our understanding of the universe. And as we'll see throughout this series, this pattern repeats again and again. The greatest breakthroughs in quantum physics didn't begin with bold new ideas. They began when careful experiments exposed the limits of what everyone thought they already knew. So here's the question to carry with you as we continue our walk. If nature keeps contradicting our best explanations, should we cling more tightly to our theories, or should we learn to trust the experiments even when they overturn everything we thought we understood? And